In this lecture, we will discuss Ampere's force law. In previous lectures, we defined magnetic induction from Lorentz force law, and then we discussed and proved the solenoidal nature of magnetic induction, which is the famous Maxwell's second equation. In lecture 3a, we spoke about Biot-Savart's law and also derived the expression of force experienced by a current element, IDR, in the presence of a magnetic induction B. Here, this equation follows from Lorentz force relation. So this is actually the Lorentz force law. Let us now state the Ampere's force law. First, why shall we study it? What is its utility? Or what information does it furnish? Ampere's force law gives expression of force of interaction between two current carrying circuits. That is, it tells us how much force one circuit exerts on another circuit. Let us emphasize that Ampere's force law is derived from Biot-Savart's law and Lorentz force equation, and this we will show explicitly. Let us first go to the statement of Ampere's force law. Consider a source circuit C prime. O is the origin, I prime dr prime is the source current element of C prime. Its position vector with respect to origin is vector r prime. This C prime, that is the source circuit, produces a magnetic induction at some point P where IDR, another current element, is located, and the expression of magnetic induction due to this source circuit C prime at this point P is given by Biot-Savart's law. Again, this IDR is a part of circuit C, which is obviously in the field of the source circuit, and hence it is called field circuit. The field current element IDR as well as the field circuit C, being in the field of the source circuit, feels a Lorentz force. So it is clear that we are using Biot-Savart's law and the Lorentz force law to develop Ampere's force law. Now, vector B due to C prime at P is given by this expression, which is Biot-Savart's law. The force experienced by IDR placed at the point P due to this B is given by the Lorentz force law. dF is IDR cross B. The total force experienced by the entire circuit will be an integration over C, and therefore we have this expression. So vector F is given by this expression, which is called Ampere's force law, which he gave in 1823. Now this is obviously the force on C, which we call the field circuit, due to C prime, which we are calling the source circuit. Let us point out one thing. In this expression, what is r cap? This r cap is the unit vector along this direction, that is from source to the field. Let us interchange the source and field now. In our discussion, this was the source and this C was the field. Now let us interchange them. Now this is a current element. It will also produce its field at the location of I prime dr prime, and therefore we can similarly write down Biot-Savart's law to get B due to IDR here, and then use Lorentz force law to obtain the total force experienced by C prime, it being in the field of C. So force on C prime due to C is written over here, and here what we have done is we have interchanged I by I prime by I, C by C prime by C, dr by dr prime, and dr prime by dr. And mu0 by 4 pi is a constant in both the expressions. Capital R representing the distance or separation will be the same in both situations. The only thing that will change now is r cap. Now the unit vector from source to field is this direction, which is therefore minus r cap. Now simplification gives us this expression. So what we have got is the forces exerted by one circuit on the other. This is the force on C due to C prime, and this is the expression of force on C prime due to C. So these are Ampere's force law. Now, having stated Ampere's force law, let us come to Newton's third law of motion, which is valid in an inertial frame and for distances larger than the quantum limit, that is atomic and molecular size. If 1 and 2 are two particles and they are exchanging forces, then action, that is the force on 2 due to 1, and the reaction, that is force on 1 due to 2, will be equal and opposite. So this is the well-known Newton's third law of motion. Ampere's force law gives expression of the force on one circuit due to another circuit. Newton's third law says that the two forces should be equal and opposite. Now we can check whether such prediction of Newton's third law follows from Ampere's force law. That is, if the two laws, Ampere's force law and Newton's third law of motion, are consistent. So consider the force on C due to C prime, and this we got, here it is. Now use the vector triple product relation in the integrand to get two terms. So this is the first term, this is the second term. As r and r prime are not connected, they do not depend upon each other. The integration involving them, that is the integration over C, that is over r, and the integration over C prime, that is over r prime, will also be independent, and it does not matter which integration is done first or which is done later. That is, the integrations can be interchanged. Then we end up with this expression, which is a part of the first term. Here in this expression, integration is to be performed over C prime first and then over C, but here the order has been interchanged, first integration over C and then integration over C prime. Now let us consider the integration over C, which can be recast in this form. Now apply Stokes theorem that converts line integral to a surface integral, bringing curl of r cap by r square as integrand. Now r cap by r square can be expressed as negative of grad of 1 by r, and so we have curl of grad coming in. Now it's a vector identity that curl of grad of any scalar function is 0. So if we put it in the integrand becomes 0. So the first term is 0 and we only have the second term. Now the second term can be rearranged, since we can again interchange the order of the integrals, and therefore we end up with this expression. So this is the expression we end up with for the force on C due to C prime. Here C is the field circuit and C prime is the source circuit. Now what will be the force on C prime due to C? This was previously derived and we got this expression. Now we can proceed similarly, that is, expand the vector triple product, interchange the order of integrations over C and C prime, and finally use Stokes theorem. Here grad prime is used since line integration is over the source circuit C prime, and the surface spanning the source circuit C prime is S prime. Also the r cap by r square is minus of grad of 1 by r, which is actually grad prime of 1 by r. This negative sign is neutralized by the additional negative sign that comes when we take derivative with respect to primes, because in vector r prime is preceded by a negative sign. This you have done in mathematical physics class. Now final use of curl grad equal to 0, which is a vector identity, gives the first term to be 0. So the calculations are here. Now writing only the second term, we have this expression. As scalar products commute, it doesn't matter which one is written first out of dr prime and dr, and therefore we can rewrite this in this way. So this is the force on C prime due to C, and this turns out to be negative of the force on C due to C prime. So let us make a gist of what we got. So what we got is that the two forces are equal and opposite. The force on C due to C prime and the force on C prime due to C are equal and opposite, having this expression. This means Newton's third law of motion is consistent with Ampere's law of circuit-circuit interaction, or Ampere's law of force. An important point to be noted is that in this calculation we have taken help of Stokes theorem, application of which was possible because we had a line integral that we converted to surface integral. The point is, we integrated over a circuit, either C or C prime. Now let us think of a problem, the same problem with current elements. In that situation, we do not have to integrate, and so line integrals will not be there, and so Stokes theorem will not help us reduce the first term to 0 as we did in arriving at these relations. So comes the question, is Newton's third law of motion valid when current elements interact? We'll address this issue right now. Consider two current elements. Now, I dr and I prime dr prime are isolated current elements and they are not part of a circuit. Let us, as before, calculate the force that I prime dr prime exerts on I dr and the force that I dr exerts on I prime dr prime using Lorentz force law and Biot-Savart's law as before. Then the force on I dr turns out to be of this value, while the force on I prime dr prime turns out to be of this value. Are they equal? In the two expressions of df and df prime, we have vector triple products and we can dissolve them to get this equation and this equation for df prime. Now obviously the first terms are unequal. Here we have dr prime, here we have dr, here we have dr, here we have dr prime. So the first terms do not match. The second terms match because dr and dr prime, the scalar product can be written in any way, so they match. And here we have minus sign and here minus minus becomes plus. But what prevents this force being equal to this force is the presence of first term. In the previous case, due to an integration, this term turned out to be 0, but here it cannot be put 0, and therefore we end up with this result that df and df prime are not equal and opposite. Let us mention an example to highlight this point. Consider I prime dr prime moving vertically and I dr moving horizontally, and their separation is vector r, so that we have these dot products, and when we put these results in these expressions, what we get is df not equal to 0, which is the force on I dr, and df prime is 0, which is the force on I prime dr prime. So we get to this result. Now this discussion raises an important question. Is this a violation of Newton's third law? Are action and reaction not equal and opposite in the situation when two current elements are interacting? We will answer this question. We will address this issue a while later. But let us make a discussion first in that direction so that we can get to the right answer. The issue is a serious one, as Newton's third law of motion is a very important law, a very sacrosanct theorem, so to say. But in science, in physics, you have to have logic to retain a law when we find that it fails in some region. Let us see the consequence of Newton's third law being violated. So what happens if Newton's third law is violated or negated? What other laws rest upon Newton's third law? As you might recall from mechanics class, conservation of linear momentum rests on cancellation of internal force, and this cancellation of internal forces was possible because of Newton's third law. Let us refer to this figure briefly. This is a system of particles and this is the equation of motion for the ith particle, and it involves an external force and an internal force. Now we get this equation only if Newton's third law is active, which says that the force exerted on the ith particle by the jth particle and the force exerted on the jth particle by the I particle cancels, and only then the internal force cancels out and we are left with the external force. Now if external force is 0, we have dp dt 0 and therefore P is conserved. So conservation of linear momentum significantly depends upon cancellation of internal forces, which was done using Newton's third law. So what we arrive at is that if Newton's third law is disobeyed, as it appears in our calculation, then we are disobeying conservation of momentum, which is a scary thought. Let us now speak about how momentum is conserved in electrodynamics. In an electromagnetic field, there is field energy, there is field momentum, and we are not discussing these things in details here, but we should keep in mind that when we speak of a field, we refer to an influence, and that influence is there through energy and momentum of the field. So even field have energy, which is called field energy. Even field have a momentum, which is called field momentum. Field momentum per unit volume is defined as Pf is epsilon 0 E cross B, where E represents the electric field, B represents the magnetic field, or alternatively the field momentum density or field momentum per unit volume can be expressed as vector S by c square, where S is E cross B by mu 0, which is a quantity called Poynting vector, which represents energy flow per second per unit area having unit of watt per meter square, and C represents the speed of light in vacuum. We will not go into the details of Poynting vector, etc., and will stick to the present topic. Let us first make ourselves sure that this Pf indeed represents field momentum per unit volume through a bit of dimensional analysis. This is the problem that we address now. We will find dimension and unit of Pf, and through that we will justify that this vector Pf, this quantity, indeed represents momentum per unit volume. We can do it starting from either of the two definitions. Let us start with this one first. This is the definition of Pf. Now put the units: Tesla for B, volt per meter for E, and farad per meter for epsilon 0. These things were addressed in lectures 1a and 3b in details. Now farad can be written as coulomb per volt, and then we use this fact that coulomb into volt is joule, and therefore simplification gives us this result. Again, if we start with this definition of Pf, then we end up with the same thing. So Pf can be expressed in these units, and if we put down the dimensions, joule is force into distance, P for second and L for meter, and therefore we end up with this combination of dimensions or this combination of units. So the first question has been answered. Now come to the second one. This can be rewritten as follows. Now this is mass into velocity, and mass into velocity is momentum. So this part is momentum, and this is obviously the volume. So indeed Pf represents field momentum per unit volume or field momentum density. It is actually momentum per unit volume or momentum density, but since it corresponds to EB, which are electromagnetic, which characterize electromagnetic field, we call this momentum to be field momentum. Now it is time to take the bull by the horn. That is, we will address the issue whether Newton's third law is obeyed or not obeyed. Now for closed circuits, the straight answer is yes. It obeys the two laws, Ampere's force law and Newton's law of motion, third law of motion, are consistent with each other. For two current elements, which are actually charges in motion, we wrote down the forces on each other as per Ampere's force law and found them to be unequal. Now, momentum by time, that is the rate of change of momentum, is force. And if forces are not equal, so is momentum. But in electromagnetic field, momentum is conserved, and this is an established truth. The current elements which represent moving charges constitute current and so generates both electric field as well as magnetic field. So the problem actually involves an electromagnetic field. So question therefore shifts to whether momentum is conserved in an electromagnetic field or not. And the answer is an emphatic yes. Momentum is conserved in an electromagnetic field. In the situation we are considering, we have matter, that is the charges, and the electromagnetic field, and we are actually studying interaction between matter and field. The electromagnetic field exerts force on matter, and we have used Lorentz force law to describe that. Matter also exerts force on the field, and the two balances. As changes in momentum cancels, forces must balance. So Newton's third law is preserved because of momentum conservation in an electromagnetic field. In a nutshell, Newton's third law appeared to be disobeyed because we did not consider the field momentum of the electromagnetic field. We can give an analogy. In a cricket match, you have to consider the contribution of all the batsmen, 11 batsmen, when wanting to calculate the total score. We cannot leave out even a single run scored by someone. Here too, when every contribution, that is contribution of matter or charges as well as of the field, is considered, momentum is conserved. And this means no net force, and hence forces must balance, which is Newton's third law. One thing, of course, strikes an inquisitive mind. We were discussing Newton's third law, its conservation or not, whether it is valid or not, and in doing that we have brought conservation of momentum into the picture. Now this shows, and finally got to the answer, this shows that conservation of momentum is a deeper principle, carrying more weight, and indeed it is so. We next discuss once again Ampere's force law, but now for parallel current carrying wires. The previous discussion was a general one. Consider a straight current carrying wire carrying current I prime, which is the source circuit, and O is the origin, a point somewhere on the wire being of infinite length oriented along k cap. P is the field point at a distance rho from the origin. The position coordinate of the field point is rho phi 0. Now field due to straight current carrying wire at P can be obtained from Biot-Savart's law. which was done in lecture 3C and is given by this expression. So we know the field at P due to this wire, source wire, and if we now place a current element I dz k hat at P, then it will experience a force because of this B, and therefore we can use Lorentz force law to calculate the force experienced. So force experienced by this current element is given by vector df, which is the Lorentz force law. Here we have written D explicitly here to end up with this expression, which involves k cap cross phi cap, and that when done properly through right hand screw relation, the product is minus rho cap, that is towards the origin. Now taking dz down, we end up with df dz, which is force per unit length. So this is Ampere's force law, which represents interaction between two parallel current carrying wires which are infinitely long. Now why did we express it as force per unit length? Let us find the total force experienced by the field circuit. A simple integration gives us infinity, because the field circuit was extended from minus infinity to plus infinity, and because of that infinite length, the total force which we got is infinity. Now that is why we express results in terms of force per unit length. Now let us discuss parallel and antiparallel currents. First, parallel currents. I prime and I have same sign. So direction of df dz is along minus rho cap. So if we hold the source circuit or source wire I prime fixed and release the field wire carrying current I, it would move towards the source wire I prime, implying attraction. So we end up with the conclusion that parallel currents attract. This diagram shows the field lines or the B lines. For a single wire carrying current I, the field lines are concentric circles, symmetric circles, but here, due to attraction, the circles will distort. The circles fill up the intermediate space densely because attraction means moving towards each other. The direction of the field lines have been shown here. They are obeying right hand screw relation with respect to the circuit. For antiparallel currents, I prime and I are opposite, and so we have attached a negative sign here, and when put in this formula, df dz is along rho cap. So if we hold I prime, the source wire fixed, and release this field wire I, then it would move away from origin. It would move away from the source circuit, implying a repulsion. So antiparallel currents repel. Clearly the field lines now speaks volumes for it. The intermediate region is now empty. They are looking away from each other, not liking each other's company. And this aversion is nothing but repulsion. Lastly, we come to the significance of Ampere's force law for parallel currents. We can define Ampere from this law. This is the law, and if we put 1 unit for I, 1 unit for I prime, the distance of separation as 1 meter, then simple calculation gives us 2 into 10 to the power minus 7 as the numeric, and here we have put the value of mu 0 to be 4 pi 10 to the power minus 7 Henry per meter, and proper consideration of units gives us this value, Newton per meter. So ampere is that current which, when flows through two infinite parallel wires at 1 meter separation in vacuum, exerts a force of 2 into 10 to the power minus 7 Newton per meter. It might be an attraction if currents are flowing in parallel, or repulsion if currents are flowing in antiparallel. And again, always we have to be careful about units. This law also gives a practical method of determining the permeability, mu 0. Suppose value of mu 0 is not known and we wish to find it through experiment. Take two wires of infinite length carrying 1 ampere of current, and they are separated by a distance of 1 meter. Then the force of interaction as experimentally found is 2 into 10 to the power minus 7 Newton per meter. Then this Ampere's law of force gives us the value of mu 0 to be of this amount, 4 pi 10 raised to the power minus 7 Henry per meter, and we have to take good care of the units to get everything right and consistent. Let us end with a quote of the famous science fiction writer Robert Heinlein. Everything is theoretically impossible until it is done. Yes, experiments say the last word in physics. Experiment has the last laugh. You have to do something in reality and not make routines that cannot be followed. Thank you.